Hello, this is the problem set video for problem set 4, task 1. And I'm going to go through the task and then through the rubric to tell you what you have to do and explain things. Um, this task is really a review of the conditionals material from our previous problem set. And it also involves a thing that you're going to do a lot in programming, which is trying to fit a little bit of your code into a broader context of other code and figuring out what do I have to do to make this work correctly. Um, so we have given you a substantial amount of code in a file called maze.py that implements a maze with a robot, and the robot can move around and use fuel. And you're asked to implement only a little bit of code in SQL.py that just implements what are called policies for the robot. So a policy is a function that takes a certain number of parameters. It takes 5 parameters, and they each have a specific meaning, although several different policy functions can all take those same parameters. And then a policy function has to return one of a few special variables that are defined in maze.py that are essentially instructions for the robot to move in a certain direction. So you can think of a policy as the decision-making part of the whole system, where we've implemented the part that draws the robot and draws the maze and implements the rules of the maze for you. So to go into that just a little bit more, here's what a maze looks like. And you can see that this is just a printed string. There's some hashtags here, and then a greater than sign and a G. Our greater than sign or other V-shaped character is going to represent the robot, and the direction of the V tells you where it's facing. So it's either a less than sign if it's facing left, greater than facing right, an exponent sign if it's facing up, and a V if it's facing down. So one of those 4 characters represents the robot, and then the goal is represented by this character G, and our goal is to get to that goal. So we want the robot to move in such a way that it bumps into that goal, and that's the end of the maze. Empty spaces represent places that we can move through. Hashtags represent walls. And finally, as the robot moves, it leaves a trail of periods behind it, or dots. And so these dots, you can move through them. You can go back and retrace your steps if you want. But typically, we want to take advantage of those to avoid that. So that's the world that the robot lives in, made of these different characters. And we have some functions that can animate the robot moving through the maze according to a certain policy. Your job is just to author the policies. The parameters of the policies. So I mentioned there were 5 parameters to make a policy function. So parameters 1 through 4 tell the policy what are the surroundings of the robot right now. And the policy has to make a decision based on that information. So you get to know what's in front, what's to the right, what's to the left, and what's behind. Right? Front, right, behind, left is the order. So it goes around in a circle clockwise from the top. And each of those comes in as a string. So you'll get the string, space, or hashtag, or G, right, or period. And those have the meanings that I just described. And then the 5th parameter to this function is an integer indicating how much fuel is left. And so every time your policy function returns a value, the robot is going to look at that value, which is going to be one of these special maze.forward, maze.right, maze.backward, maze.left values. It's going to look at that value and say, oh, you want me to go left? Okay, I'm going to move left. And that's going to happen. However, that changes the state of the maze is depending on the robot's position and what's to the left of it, for example. And during that activity, it spends 1 unit of fuel, whether or not anything happened. So if you're facing into a wall and you just keep saying forward, 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 you can use up all your fuel bumping into that wall over and over again, and nothing's going to happen. And so the 5th parameter, the fuel, is used to basically tell us like how far can we still travel. Most of your policies can safely ignore that parameter, but it can be useful for certain kinds of random policies if you want to explore that area. As I mentioned, to be a correct policy function, you have to return one of these 4 variables. If you return any other value by accident, like none, because you fell out of a bunch of conditionals and didn't have a return statement yet, then the robot explodes. So we don't want that to happen, right? So make sure that your policy functions, if they have multiple branches, which they will of conditionals, that each branch has a return in it. Okay, here is an example policy function. It's called the turnaround policy. And the code says, right, it's a function called turnaround policy. It accepts parameters ahead, right, behind, left, and fuel. It says if, and then there's this is not wall function call here. We give you two predicates, is not wall and is not visited, that you can use to apply to one of these characters to get a Boolean value, true or false, that can help you make your decision. So you could do some tests involving the character to figure out what it is, but you can just use the provided is not wall function if you want to get a Boolean is whatever's in front of me not a wall, right? A goal is not the wall, a visited place is not a wall, a space is not a wall. All those three things are places that you can move into. So in this policy, we say if whatever is ahead of us is not a wall, then our policy is, right, the result of our policy is go forward. And then otherwise, if there's a wall ahead of us, we're going to return backward. And this gets into something that happens. So when you return a direction other than forward, the robot is going to turn to face that direction and then move one unit in that direction if it can. Both turning and moving are part of the same command. If there's a wall in that direction, it'll still turn to face that direction. And so when we say return maze.backward here, the next step of the robot is going to call this policy function again, and the robot will have turned around, so forward will be facing the other way. It'll say, oh, there's not a wall ahead of me, I guess I'll go forward. So this policy is going to bounce back and forth. It's not a great policy for solving mazes, but it does illustrate how a policy function works. Okay, so the maze.py file has multiple functions that you can use for seeing your robot in the maze. There's one called trace surroundings that prints out a bunch of information about the surroundings of the robot as it moves. There's one called animate text that actually prints out multiple blocks of text showing the state of the maze as the robot moves. And finally, there's one called animate turtle that uses turtle drawing commands to draw the robot as it moves through the maze. These functions take 4 parameters: a maze, a policy, a fuel budget, and an animation speed. And so this describes all the details of that. You can read that on your own. We've provided some testing code that's commented out in the file that uses these functions properly, so you can look at how that works. A twist here is that the policy is a function, right? But we're using it here as a variable, which is something that you can do in Python. So your job is to write 3 policies. It's not actually that much work. First, a bounce policy. And what the bounce policy should do is it should always move forward if it's not blocked. If it's blocked ahead, then it should turn left. Or if it can't turn left because there's a wall there too, it's in a corner like this, then it should turn right. Finally, if it's blocked on all 3 sides, like it hit the end of a dead end, it should turn around and go backwards. And this simple policy, which sort of moves when it hits a wall, it sort of bounces and turns and keeps going. This can actually solve some labyrinths, which are mazes without branches. But it gets stuck in most true mazes. It's easy for this policy to get stuck going in circles. Your bounce policy has to use the isNotWall function to determine where walls are. And it must not use the isNotVisited function, which is the other predicate that we provide you with. So we have output examples here. I'm not going to go into them here, but I'll just show you briefly. Here's what trace surroundings look like. So it has a big text output of, it shows you the state of the maze at the beginning, it shows you what happens at each step, and then it shows you the state of the maze at the end. This is useful for figuring out if your robot doesn't do what you want, why it may have done that. And then the animate maze output is just printing a bunch of stuff. And if you run this in the console, it's animated because as you see it scroll down, you'll see the robot move step by step. But this shows each step along the way to the goal. And finally, the animate turtle animation is, again, the same thing, except now it's sort of an animation that plays in real time. Okay, so In addition to the bounce policy, you need to implement the left wall policy. So this implements a left-hand rule for solving mazes. You always keep your hand on the left wall, and you will eventually reach the goal. Specifically, the rules are as follows. So if there's no wall to the left, we move left. And that's our first priority, is moving left whenever we can, not going forward. If there's a wall to the left and there's no wall in front of us, we move forward. If there are walls to the left and ahead of us, but there's no wall to the right, we move right. And guess what? If there's walls, all three directions, we move backwards. Now, this policy is pretty similar to the bounce policy that you just implemented, but it gives the robot a totally different set of behavior. And in fact, this policy is rather good at solving a lot of different kinds of mazes, right? You just keep your hand on the left-hand wall, you keep moving, and unless there's some sort of like island that you can go in circles around, you're going to solve the maze. So, again, the left wall policy must use is not wall and is not allowed to use is not visited. There's more reference results here. I'm not going to go into them in this video. A custom policy is the third policy you have to implement. And the restrictions are as follows. You have to use at least one if statement in that function, not in some other function. It has to call either left wall policy or bounce policy as sort of a sub policy in some branch somewhere. And it has to return the result of that policy in that branch. But that should not be all that it does. And then, for 100% credit, if you want the extra goals, your custom policy must be able to solve at least 3 of the 6 harder mazes. So there are multiple maze variables defined in maze.py, like maze 4. And mazes 7 to 12 are a little bit more tricky than the easier ones that some of the simpler policies can solve. So your job is to try to find a policy that can solve at least 3 of those 6 harder mazes, and there's lots of ways to do this. And it'll have 300 fuel to solve the maze, which is like more than enough to go back and forth all over the maze. The mazes are not that big. Your custom policy is allowed to use randomness if you wish. You can import that random module. If you do, that means the robot might not always be able to solve the maze. So what we do is we give your robot a bunch of tries to solve the maze. And if it can solve it at least 50% of the time, we count that as good enough. That counts as solving one of these harder mazes. So, as I mentioned before, there's automatic testing at the bottom of the file. You can uncomment some of those to do the tests. You can also call some of these animation functions in the shell to test your policies. And that's the big picture. So, it's really important to understand how your policy function fits into the bigger picture of the maze.py file. That file has a bunch of code in it that has some loops in it and some other stuff going on to do all this printing and animating and whatever. And your policy fits in a very specific place, right? So every time the robot needs to decide what to do, it'll call your policy and it'll tell your policy, hey, here's where I am. What do I do, right? And notice that your policy only gets to know what is immediately around the robot, right? It doesn't get to remember where the robot has been, except if it sees those dots. That's a hint. It doesn't get to sort of, plan or make multi-step decisions. We're not actually interested in an algorithm that sort of looks at the maze from an eagle's eye perspective and finds a path to the goal. We're interested in a policy where if we put the robot in a maze that it can only see its immediate surroundings, it can nevertheless navigate to the goal with some reasonable efficiency. Each time your policy function returns a value, the value is used to move the robot, and 1 unit of fuel is used up, as I mentioned before. And if there's a wall blocking the direction, we'll turn to face that direction, but we won't move because obviously we can't. We'll still use a unit of fuel. If the robot runs out of fuel, then that counts as failing to solve the maze. So the 4 parameters to the policy function should be passed into is not wall or is not visited, or if you want, you can test their values directly. And the turnaround policy that we showed you has an example of how to use is not wall. And then, as I already mentioned, if your policy returns none, the simulation will crash. So you need to make sure that this will not happen. Otherwise, things will not go well. So let me open up the rubric here and walk through that quickly, because this is how you will be graded. Step 1, all functions are documented. This is our usual goal. Step 2, the results of balance policy should be correct. So we're just going to test your policy, and the policy has a very definite definition that says this is what it should do in these situations. So we don't even need to run it through a maze. We can just say, oh, for these inputs, what does your policy do? We will test the left while policy in the same way. And then here are the definition requirements. So you have to define balance policy. You must call is not while. You must not call is not visited. Same two sub-requirements for the left while policy. And then for the custom policy, it has to use an if statement. Nothing beyond that for the core goals. For the extra goals, we're going to do more tests of balance policy and left while policy. Some more maybe not quite so obvious situations that the robot could find itself in, and there's a defined correct result in those situations, and we're going to test for it. Here's this goal that the custom policy solves at least 3 difficult mazes, solving them in at least 50% of attempts. In terms of our definitions, we have some extra goals. So one is that the balance policy does not use any comparisons, right, and uses this is not while predicate instead, and the same for the left while policy. Finally, in the custom policy, there's this extra goal that you must call balance policy or left while policy in at least one place as like a sub-policy. And that's sort of to push your understanding of how can these different functions that have similar parameters and similar return values fit together in a nice way. So that is task 1 of problem set 4, and I will record more videos for the other tasks.